And now we are going to answer this question about the separation of neutrals and anions. So here you have the representation to understand the separation, the separation of neutrals and anions. And we are going to speak now about the electroosmotic mobility. I repeat, when I consider my compound, this is the electrophoretic mobility. When I consider the background electrolyte and the movement of the background electrolyte, this is the electroosmotic mobility. So what's the electroosmotic mobility? You have the background electrolyte, which is the salted solution with the conductivity. So you understand that here in the background electrolyte, you have different salts. This is not the sample, this is only the salt to allow the conductivity. And we work in bare fuse silica capillary. It means that in the inner surface of the capillary, this is only silanol group. So I can represent this like this. You see, we have only silanol group in the inner surface of the capillary. And there are some properties of the silanol group very interesting to understand the electroosmotic mobility. Indeed, depending of the pH value, we can have the protonation or the deprotonation of the silanols. So on a bare fuse silica capillary, we are in acidic condition. For example, we consider acidic condition. In that case, the SiOH group are protonated. So we have a protonation of the silanol SiOH. And then the surface net charge is equal to 0. So in that case, nothing happens. We have only the electrophoretic mobility. But in basic condition now, we have now the deprotonation of the silanol group. And then the deprotonation imply a surface net charge less to 0, a negative surface net charge. And then it changes everything in the inner surface of the capillary, because now you have a different equilibrium in the inner surface of the capillary. So the surface net charge, depending the pH value of the background electrolyte, and you will see that this pH value is very important to control this phenomena. So the electroosmose, or the electroosmotic flow, is based on a phenomena in the inner surface of the capillary and due to the presence of silanol. You have a charged capillary surface, and plus, of course, the neutralization of the opposite charge of electrolyte. Meaning that at the capillary surface, you have a charge of a neutral, an anionic charge due to the deprotonation of silanols. And then when you have a deprotoning charge, you need to neutralize this charge with what? With the sample, the salt in the background electrolyte. If you have salt in the background electrolyte, it means that you have cations and anions. And then you have a different equilibrium in the charge, in the inner surface of the capillary. And you have a phenomenon named double layer. So it provokes a displacement of the solvent that occurs under the effect of the electrical field. So if I show you with the schematic representation of the capillary, the phenomena of double layer, here I have a bare fuse silica capillary at acidic condition. If I am in acidic condition, you understand that I am deprotonated, and then I have a negative charge surface between the cathode and the anode, of course. So all the surface. So I represent now the surface like this. You understand that this represents the negative silanol, and we have a negative charge on the surface. So this is the surface of the capillary. You have the detectors and you have the negative charge. We know that we work in basic conditions. So I fill, of course, the capillary with the background electrolyte, which is a salted solution, and it needs this because we have conductivity. And it means that in that background solution, I have cations and anions to perform the salted solution and to allow conductivity. So you see now, this is the zoom in the electrolyte, in the background electrolyte. You have different cation and different anion, and there are equilibrium, a neutral equilibrium in the solution you can have generally in your different solution. But we consider now the inner surface of the capillary. And at this place, you see that there are a disequilibrium because the cations of the solution are attracted with the anion of the capillary wall. This is not the case, of course, with the anion because this is a repulsive interaction. Then, when we apply the voltage, we have a disequilibrium just at the interface with the capillary. And this disequilibrium allows the movement of the background electrolyte. And there are the creation of an anion movement due to the formation of a double layer, ionic layer. You see the first layer, which is a stable layer, and you also have a diffusion layer, which allow the movement of the ion movement in the solution, and this ion movement is named the electroosmotic mobility. It means that each sample, each solution are attracted by the anode if I applied a voltage. I have the movement of the background electrolyte. You see, it is represented by this mu EO arrow. So you have the electroosmotic flow, and all the compounds are follow this electroosmotic flow. So to understand, to calculate the electroosmotic flow, we have a better manner as this, but just to understand what is the electroosmotic flow and what depends the electroosmotic flow, the decrease of the double layer potential determines the velocity of solvent, the velocity of the solvent, and then of course the electroosmotic mobility. The velocity is depends on this ratio, the electric constant of the electrolyte, and of course the zeta potential, which is the potential which represents the net charge of the surface. And of course here you have the electrical field. And it depends, of course, of the viscosity, because that's quite normal. The viscosity of the system, of the solution, is very important. So the electroosmotic mobility is quite similar to the velocity, but without the electric field. And then the electroosmotic mobility depends on the ratio dielectric constant time potential zeta over 4p nu, the viscosity. So of course there are an influence of the pH on the silica group of the capillary. We have a bare fused silica capillary, and then the pI is around 2, but you have to understand that it increases the electroosmotic mobility is due to the surface net charge of the capillary. So we have to see the silica group and the protonation, or the protonation of the silica group. And this is influenced by the pH. Then when we increase the pH of the solution on 2 to 9 on pH, we increase the charge density of the inner surface of the capillary. So here at pH 2 we have protonated compound, protonated silanol group, so we have a very low electroosmotic flow. And if we increase the pH, we have deprotonation of the silanol group, and then of course the charge is higher as compared to the pH, the low pH, and then we have a high electroosmotic mobility. It is very simple to understand. So we can control the electroosmotic mobility with these parameters. For example, if I work at 8.9, I have a huge electroosmotic mobility, and if I have a 2.2, for example, in acidic condition, I have a small electroosmotic mobility. And this is this allows the separation and to perform separation. So now you have to understand that we take again the same example with a cation, a neutral compound, and an anion. And we are in a bare-fused silica capillary at basic condition. So we have what? We have deprotonated silica capillary, and then we have, of course, the electrophoretic mobility of our compound. And remember, the cation has an electrophoretic mobility in that direction, the anion has an electrophoretic mobility in that direction, and the neutral has no electrophoretic mobility because there is no electric force. But there are also an electroosmotic mobility which is applied to every system. Every compound have this electroosmotic mobility. So now you see that each compound has different mobility. And then we can see the compound, because I detect the compound. I have the cation, of course, because the electrophoretic mobility and the electroosmotic mobility has the same direction. The neutral, because we have only the electroosmotic mobility, and then we can detect the compound. However, it is not possible to separate the neutral compounds. And the anionic compound, with the possibility to see the anionic compound if the electrophoretic mobility is lower than the electroosmotic mobility. And you have, in that case, first the neutral, second the neutral, and first the cation, I'm sorry, second the neutral compound, and third the anion compound. It is not possible to have a neutral one, a cation one, an anion, plus a neutral, etc. You have always the family. So first the cation, second the neutral compound, and third the anion compound. And the apparent mobility I can detect, I can calculate, is the mobility of the compound, taking into account the two mobilities. So it is the apparent mobility is equal to the effective, electrophoretic mobility of the compound plus the electroosmotic mobility of the compound.